First, we load the necessary libraries. These packages will help us retrieve financial data, perform state space modeling, fit ARIMA models, and conduct residual diagnostics. Next, we fetch the price data for the QQQ ETF from Yahoo Finance, specifying a date range starting from January 1st, 2022. To ensure the dataset is clean, we remove any missing values. Now, we define the variance matrices for the level and slope components of our model. These matrices help in specifying the noise structure of our state space model. Next, we extract the smoothed estimates and ensure they are in the correct format for plotting. If the alpha hat component is found in the smoothed object, we proceed to create a time series of the smoothed estimates. Now, let's also explore an ARIMA model. We fetch the adjusted prices of the QQQ ETF and convert them into a time series object. We use the auto-ARIMA function to automatically fit the best ARIMA model to our time series and then forecast the next 10 periods. The results are plotted using autoplot. The auto-ARIMA READI11 model shows the Nasdaq as represented by QQQ trending up. Next, we'll compare this with a structural state space model using struct_TS. First, we fit the model to the closing prices of QQ. We then plot the actual closing prices. We forecast the Kalman filtered structural trend model with autoplot for 10 periods forward. Finally, let's perform a Ljungbox test to check the residuals of our model. We load the QQQ data from Yahoo Finance starting from January 1st, 2010. We plot the original series and its differenced version to inspect the data. We then plot the ACF and PACEF of the differenced series. Next, we perform the Ljungbox test on the differenced series to check for autocorrelation. Let's break down what this result means. Q. This is the test statistic, which is 77.839 in this case. A higher value indicates more evidence against the null hypothesis of no autocorrelation. DF. This stands for degrees of freedom, which is 9 here. It represents the number of lags minus the number of parameters estimated in the model. P-value. The p-value is 4.338e13. This is a very small number, much smaller than the typical significance level of 0.05. Interpretation: null hypothesis. The null hypothesis for the Ljungbox test is that there is no autocorrelation in the residuals up to the specified lag, in this case 10 lags. Test statistic, Q. The test statistic value is high, 77.839. Suggesting that there is evidence against the null hypothesis. Degrees of freedom, DF. The degrees of freedom is calculated based on the number of lags and the parameters in the model. P-value. The p-value is extremely small, 4.338e13, which is far less than 0.05. This indicates strong evidence against the null hypothesis, suggesting that there is significant autocorrelation in the residuals. Conclusion: The Ljungbox test result suggests that the residuals from our ARIMA 0.1.1 model with drift are not independently distributed and exhibit significant autocorrelation.